Welcome to the deep dive. Okay, let's unpack this. Today we're plunging into the static world of electrostatics. It's that foundational pillar of electromagnetism, right?
Exactly.
And we want to extract the vital insights from the Feynman lectures on physics for you. Our mission, basically, is to navigate some, well, fascinating but pretty dense material.
It definitely is.
Give you the clearest understanding. So while all of electromagnetism ultimately lives within Maxwell's equations,
It's just the whole picture, yeah.
we're starting with its simplest case,
Yeah.
the elegant bit, where nothing changes over time.
That's precisely it. You know, when charges are permanently fixed in space, or maybe if they're in steady, constant motion.
Like in a simple circuit.
Right, exactly, like electrons flowing steadily.
Yeah.
Then all the terms in Maxwell's equations that involve time derivatives, they just vanish.
Okay, they drop out.
Yeah, they drop out.
Okay.
And this beautiful simplification lets us consider the electric field, the E field, completely separate from the magnetic field. And what's fascinating, I think, is that this makes electrostatics and, magnetostatics too perfect for really getting a handle on the mathematical properties of vector fields
Before it gets messy.
before they become, inextricably intertwined in the more complex dynamic situations.
Okay, so if we're building from the ground up, we have to begin with Coulomb's law.
The very beginning.
It seems remarkably straightforward.
Yeah.
This law, it basically tells us the force between two charges at rest.
Mm-hmm.
It's directly proportional to the product of their charges.
Makes sense. Bigger charges,
Yeah.
bigger force.
And inversely proportional to the square of the distance between them.
The famous inverse square law.
Right. And there's that constant involved, usually written as 1/4 pi epsilon naught, a dollar or a
It's
pascal.
strummativity of free space.
What does that actually, represent physically?
Well, it essentially quantifies how an electric field interacts with a vacuum. It affects the strength of the force. Its value is roughly $9 times 199.9 Newton meters squared per Coulomb squared. Big number.
Okay. And this is where the real power starts to emerge, right? What happens when you have more than just two charges?
Ah, yes. That's the beauty of the principle of superposition.
Right.
It states that the total force on any single charge is simply the vector sum, and vector is key here.
Direction matters.
Absolutely. The vector sum of the Coulomb forces from each of the other charges acting independently.
So they don't interfere with each other's basic force calculation.
Exactly. You just calculate each force pair and add them up like arrows. Think about it, no matter how complex the situation, like a tiny dust particle or, the huge charge separation in a lightning storm.
Wow. Yeah.
All the forces involved fundamentally break down into these two, surprisingly simple rules.
Coulomb's law and superposition.
That's it. Conceptually, these two facts are all there is to electrostatics, really. All the more complex equations we'll talk about. They're just different mathematical ways of saying the same thing.
Okay, so if Coulomb's law and superposition are truly all there is at the heart of it,
Fundamentally, yes.
why bother introducing a whole new concept? Like the electric field, FLPEB, it feels like an extra layer.
That's a great question. While it's conceptually simple, actually calculating forces with millions of charges using just Coulomb's law gets, cumbersome.
I can imagine.
The electric field, FLPEE, it isn't really a new physical thing, but more of a conceptual tool, a useful abstraction.
Yeah.
We define it as the force per unit charge that would be felt at a specific point in space.
Ah, so it describes the influence even if there's no charge there to feel it.
Precisely. It lets us describe the influence of charges on the space around them, whether or not a test charge is actually present.
Okay.
For individual point charges, you just sum up their contributions vectorially again. But for charges spread out in what Feynman calls a continuous smear.
Ah, I like that phrase.
Me too.
Hello?
It means they're distributed smoothly through a volume or over a surface, Then we use integrals over the charge density.
An integral is just how much charge is packed into a little bit of space.
Exactly. How much charge per unit volume, usually.
I see. So it's a shift from thinking about forces between charges to thinking about how charges modify the space around them.
That's a perfect way to put it.
But the source warns that calculating the E field directly using those integrals, it's often, quote, strictly a job for a computing machine.
Feynman's way of saying it's often really hard.
Yeah, which implies there's got to be a smarter way, right? A more elegant approach for complex setups.
Exactly. And that's precisely where the concept of electric potential comes in. It's the elegant workaround.
Okay, the potential. So what is this electric potential?
Well, it's related to the work done Specifically, the work done when you move a charge from one point to another against the electrical forces.
Like pushing something uphill against gravity.
Very similar analogy, yes.
Mm-hmm.
And here's the really profound insight for electrostatics. The work done to move a unit charge between 2 points is independent of the path you take.
Whoa. Okay, path independence. That sounds important.
It's crucial. It's not just a mathematical convenience. It's the fundamental physical condition that allows us to even define a scalar potential for electrostatic fields.
Why is it so fundamental?
Because if it did depend on the path, you could, go around a loop and gain or lose energy from the field itself.
Which would violate energy conservation.
Exactly. But for electrostatic fields, the forces are radial, energy is conserved, so the work is path independent. It's the bedrock for potential energy in electrostatics.
That path independence idea is really clicking now.
Mm-hmm.
So, because of this, we can define this scalar field, the electrostatic potential, the bedroll.
Right. Scalar, not vector. That's a big deal.
And for a single point charge,
Yeah.
it's just Q4 feet dollars. Simple.
Much simpler than the vector field expression, yeah.
And does superposition apply here too?
It does, which is incredibly convenient. The total potential from many charges is just the simple sum, not vector sum, just arithmetic sum of the potentials from each individual charge.
So that's the practical advantage.
Absolutely. Calculating potential is often much, much simpler than calculating the electric field directly. Potential is a single number, a scalar.
So maybe one integral instead of three.
Often, yes. One integral versus potentially 3 coupled integrals for the vector components of double PE. It's a huge conceptual shortcut and a major computational win.
Okay, great. We found this simpler way, potentially, using potential phase. But how do you get back to the actual force, the electric field? Once you have the potential, you still need the field sometimes.
It's remarkably direct. It's just a derivative. The electric field, FLPE, is simply the negative gradient of the potential.
So FLPE, Nobel-Phi.
Exactly. FLPE is a Nobel-Phi, and for anyone maybe a bit rusty on vector calculus, gradient conceptually just means finding the direction and rate of the steepest increase in potential.
Okay, the direction it changes fastest.
Right. And the negative sign tells us the E field points in the direction of the steepest decrease in potential. Points from high potential to low potential.
Like water flowing downhill. That analogy works well.
It does.
And what's the sort of deeper implication here? The fact that the E field can be written as a gradient.
Well, the profound physical implication is this. If FLPE is indeed the gradient of a scalar field, like phi LA, then its curl must be 0.
$1 times FLPE equals 0.
That's it. And conceptually, curl tells you how much a vector field tends to swirl or rotate around a point.
Like a whirlpool.
Yeah, sort of. Electrostatic fields don't swirl like that. They just point outwards or inwards from charges. So their curl is 0. And this isn't just some mathematical curiosity.
It's physics.
It's physics. It's actually one of the fundamental Maxwell equations for electrostatics. FLP-OF, FLP-0. Wow.
And where does that zero curl property come from, fundamentally?
It comes directly from the symmetry and the purely radial direction of the basic electrostatic force from a point charge. It implies that if you move a charge around any closed loop and come back to the start, the net work done by the field is 0.
Path independence again.
Exactly. It's all connected.
Okay, that zero curl property feels deeply important. Now, let's shift gears slightly and talk about the specific inverse square nature of the force, the 42.
Right.
The source, Feynman, warns us against just thinking it's natural because, things spread out like light from a bulb.
Yeah, he cautions against that intuition.
And he says, don't confuse this with actual bullets or some kind of flow of energy. What's the misunderstanding he's trying to prevent there?
It's a really common misconception, actually, to visualize field lines as if they were like physical tubes or streams carrying something.
Like water pipes.
Sort of, yeah. Feynman's emphasizing that the inverse square law is about how the strength of the field's influence diminishes with distance squared. It's not about a physical flow of particles or energy density in that simple way.
Okay, it's a mathematical description of strength, not a physical flow.
Precisely. And we use the concept of flux to capture this spreading out idea more rigorously. Flux is the integral of the component of the electric field that passes perpendicularly through a surface.
Like how much field pierces the surface.
That's a good way to think about it. The normal component integrated over the area.
So here's a key point from the text. If you take any closed surface like a balloon, say that doesn't enclose any charge.
Completely empty inside.
The net flux of coral phi E out of that surface is exactly 0.
Makes sense, right? Whatever field lines go in must also come out if there's no source or sink inside.
Right, no source, no net flow out, it balances.
Exactly. But, and here's the crucial insight from the inverse square law. If the surface does enclose a net charge, say a point charge dollars,
Now there's a source inside.
the total flux outward through that closed surface is Capesol.
Just curvature divided by that constant tape. So
Yep. And the truly remarkable part, the kicker, is that this value, Capesol, is completely independent of the shape or size of the surface you choose.
wait, any shape. A sphere, a cube, a lumpy potato shape.
Any closed shape you like, as long as it encloses the charge dollars, the total flux is always a Capesol.
How is that possible?
It's derived by first proving it for a simple sphere centered on the charge, where the math is easy because of symmetry. Then you argue that deforming the sphere doesn't change the total number of field lines passing through it ultimately. It relies directly on the 100-to-2 nature.
That's amazing. And that leads us to Gauss's law.
Directly to Gauss's law, which states, the total flux of FLPEDLO out of any closed surface is equal to the total charge inside that surface divided by epsilon.
So if I understand this right, unlike the zero curl property, which came more from the direction of the force,
So radial symmetry, yes.
Gauss's law directly depends on the force law being precisely inverse square. That specific 1 or 2 dependence.
You've got it exactly. If the exponent wasn't precisely 2, Gauss's law in this simple partial form wouldn't hold. It's fundamentally a restatement of Coulomb's law, but in terms of flux and enclosed charge.
Wow.
And just to complete the picture, in its differential form, Gauss's law becomes a nabla FLP.
Now Gauss's divergence.
Right. Divergence, FLPDI, conceptually tells you how much a vector field spreads out or diverges from a point.
Like a source.
Exactly like a source. This equation tells us that electric charges are the sources, or sinks, if field K is negative, of the electric field. Where there's charge, the field lines begin or end.
So we started with Coulomb's law and superposition,
Just those two,
and derived FLP0 and FLP0 social.
which are the two fundamental Maxwell's equations for electrostatics. We've essentially built it all up from the basics.
That's incredibly elegant.
Ah.
Okay, to show just how powerful Gauss's law is in practice, let's talk about a classic problem. Finding the E field outside a uniformly charged sphere.
Ah, yes. A standard but very illustrative example.
The text mentions that Newton struggled for years to prove a similar theorem for gravity, that the gravity outside a sphere acts as if all the mass were at the center.
He did. It was a major mathematical challenge using his methods.
But with Gauss's law for electrostatics, it becomes simple.
Incredibly simple. Almost trivial by comparison. You choose a spherical Gaussian surface outside the charged sphere concentric with it.
Exploiting the symmetry.
Exactly. By symmetry, the E field must be radial and have the same magnitude everywhere on your Gaussian surface. The flux calculation becomes just E times the surface area of the Gaussian sphere.
So V times 4R22.
Right. And Gauss's law says this flux equals the total enclosed charge, Q dollar, divided by epsilon. So V times 4 torr equals Q dollar R2.
You just solve for E.
Rearrange it and you get VD Q44 R2 dollar, which is exactly the field of a point charge Q dollar located at the center.
Wow. Done in like 3 lines of algebra.
Pretty much. You know, when I first learned Gauss's law, it really felt like getting a magic wand for these symmetrical problems that would be absolute nightmares to solve with direct integration.
Yeah, I can see that. It's a prime example of the efficiency and elegance the law provides.
Definitely.
Okay, so these fields, potentials, flux, they're powerful mathematical ideas. But they're invisible, right? Abstract. How do we actually visualize them, get a feel for them?
That's where the geometrical tools come in handy. Field lines and equipotential surfaces, they help us build intuition.
Right, field lines. Those are the lines that are everywhere, tangent to the electric field, showing its direction.
Exactly. They show you which way a positive test charge would be pushed. And their density, how close together the lines are drawn, represents the field's strength. More lines per unit area means a stronger field.
And they start on positive charges and end on negative charges.
Correct. Or they go off to infinity if there isn't an opposite charge nearby.
Okay, and then equipotential surfaces.
Those are surfaces where the electric potential, Abel-Biagel, is constant. Like contour lines on a topographical map show constant altitude, these show constant electric potential.
Ah, okay. Like lines of equal voltage.
Precisely.
And there's this really neat relationship between the field lines and these surfaces, isn't there?
Oh, absolutely. A beautiful one. Equipotential surfaces are always perpendicular, always at right angles to the electric field lines where they cross.
Always perpendicular. Why is that?
Well, remember, FLPE, nullify. The gradient, noble phi, points in the direction of the steepest increase in phi.
Right, uphill.
So FLPE points in the direction of steepest decrease, downhill. That direction of steepest change must be perpendicular to any direction where there is no change.
Ah, and a direction of no change is along the equipotential surface.
Exactly. If you move along an equipotential, Filer doesn't change, so your displacement must be perpendicular to the gradient and thus perpendicular to DFLPE.
That makes perfect sense. But wait, there's a challenge mentioned. While superposition itself is mathematically simple, just adding potentials or fields,
Yeah, addition is easy.
visualizing the combined field lines is tricky.
It really is. Field lines from different charges can't just cross each other because the field at any point has only one unique direction.
Right, the vector sum has one direction.
So the lines have to bend and merge and interact in complex ways. You can't just overlay the pictures of field lines from individual charges.
You actually need to solve it mathematically first.
Often, yes, you need to calculate the total potential or the total field first, and then you can accurately draw the resulting field lines and equipotentials. It's surprisingly non-intuitive sometimes to combine them visually.
Wow, what a journey we've taken. We've gone from the simple elegance of Coulomb's law
Just what intuitive.
through the power of electric potential and its link back to the field via the gradient
SFLPE.
to the incredible generality of Gauss's law relating flux and charge.
FLPE, FLPE.
And finally, touching on the beauty, but also the challenges of actually visualizing these invisible forces with lines and surfaces.
It's quite a structure.
And you can see how something that initially seems like, Feynman's job for a computing machine
Those messy integrals.
can actually be tackled, or at least understood more deeply, with these clever insights and fundamental principles like symmetry and path independence.
Absolutely. And think about how these concepts that sound different, force, field, potential, flux, are actually all deeply interconnected.
Different views of the same thing.
Exactly. Each gives you a different lens, a different tool to understand the fundamental laws governing static charges. And really shows how simple rules, like that inverse square law, can have such profound and far-reaching implications. They unlock these complex problems with really elegant solutions sometimes.
It's truly remarkable. So let's leave our listeners with a thought. Consider how this deep dive into charges at rest, into electrostatics,
The unchanging case.
provides the absolute essential groundwork for understanding the entire dynamic universe of electromagnetism. When these fields are no longer separate, when E and B fields start influencing each other, changing in time,
Creating waves.
their interactions drive everything from radio waves to the light you're seeing right now. What more can we unlock when we finally allow these charges, these fields, to move and change?